So what that tells us is every little model of the atom where we see these electrons orbiting in these nice little orbits is actually wrong. And so that's where we get to this quantum mechanical model. So this is our whole idea of uncertainty. We can't know exactly the position and the momentum of a particle at a given time. The more closely you get to an accurate measurement of one of them, you get less accurate on the other. And that was explained in the video that we watched. So instead of having an orbit, we moved to this idea of an orbital, which is kind of an area of space that we know that we can predict the electron would be in. So instead of knowing that it orbits in a specific location, we then just give it kind of an area. So the example we talked about is kind of like a fly buzzing around a piece of fruit. When you look at just the fly, it kind of looks like it might be orbiting in one specific pattern, but if you tracked it over a long period of time, you would actually see that it makes more of a shape. And so those shapes become our orbitals. So now we've moved from the idea of an orbit to an orbital. So our quantum model leads us to a set of what we call quantum numbers, which are really just arbitrary numbers that are given to classify different orbitals or electrons. So we can get as specific as a certain electron. So we have 4 total quantum numbers. The first quantum number is the principal quantum number, and we use the variable n to represent that. And the principal quantum number is just integral value starting with 1 all the way up to 7. So we can really say that this stops at 7. So that's the location of the energy level, so that principal energy level. So as n gets larger, the electron is spending more time farther from the nucleus, and so this is also a higher energy level. So the principal quantum numbers are what you think of when you look to the left of the periodic table and we see the numbers 1 through 7 for what we have called our periods or our rows. So those are our principal quantum number or the principal energy level. So your only options for this number are 1, 2, 3, 4, 5, 6, 7. And you can think of that as that generalized shell as we're getting further and further away from the nucleus. Our next quantum number is L. So it is what's called our angular momentum quantum number. That's not super important. What this relates to is our subshells or our sublevel. So this can be anywhere from 0 to n-1. So what that means is that there's only certain sublevels on each principal energy level. So this is the first part that's really important. So for for principal energy level, n equals 1. The L can only be 0 to n-1. So 1 minus 1 is 0. So the only angular momentum number is 0. When L of 0 is an s orbital. So on our first principal energy level, we only have an s orbital. So on n equals 2, L can be 0 or 2 minus 1, which is 1. So that corresponds to an s and a p orbital. For n equals 3, L can be 0, 1, or 3 minus 1, which is 2, and that corresponds to S, P, and D. So what that means is that on our first our first principal energy level, we can only have the sublevel S. For our second one, we have an S and a P, and for our third, we have S, P, and D, and then if we kept going forth, could have S, P, D, and F. So our first is just our principal energy level, and then our second is which actual sublevel or orbital are we in? Are we in an S, a P, a D, or an F? Our third quantum number is the magnetic quantum number, which is represented by M sub L. And the available numbers for that is the integral values between negative L to positive L, including 0. And this is just the orientation. So our first, if you remember, our first L is 0. And that's for an S orbital. Well, you can't have negative 0 or positive 0. So for an S orbital, we only have one orientation. And that makes sense because an S orbital is a sphere. So there's really only one way to orient a sphere. And so there is only one M sub L number for an S orbital, and that is 0. But for P, if you remember, L is equal to 1. So then M sub L can be negative 1, 0, and positive 1. That corresponds to the 3 orientations possible for a P orbital. Because you see a P orbital is shaped kind of like a dumbbell, and it can be oriented along the x-axis, the y-axis, or the z-axis. And so that gives us 3 orientations, so that gives us 3 separate P orbitals. If we were looking at a D orbital, that's going to be an L equals 2. So then the M sub L options are negative 2, negative 1, 0, positive 1, positive 2. So that gives me 5 different orientations of a D orbital, which you're used to hearing that there are 5 D orbitals. And then finally for F, which is L equals 3, which means that M sub L is negative 3, negative 2, negative 1, 0, plus 1, plus 2, plus 3, which tells me that there are 7 total F orbitals. So we have 1 orientation of an S orbital, we have 3 orientations of a P orbital, 5 of a D orbital, and then 7 of a F orbital. Our last quantum number is our spin quantum number. That is related solely to the electron that's inside that particular orbital. So that's M sub 2. The only options is either negative 1/2 and positive 1/2, because one electron has to be spinning in one direction and one has to be spinning in the opposite direction for them to be side by side within an orbital. So what this leads to is that there are a max of 2 electrons in an orbital. All right, so those are our 4 quantum numbers. So these are all of our orbital shapes. So remember how we talked about that. There is 1 S orbital, there are 3 P orbitals, 5 D orbitals, and 7 F orbitals. You can fit a max of 2, so there are 2 total electrons that can fit in any S orbitals on a level. We could get a total of 6 electrons in a P, total of 10 electrons in a D, and 14 electrons in F's. Excuse me, I was saying AD, in all of the D's or in all of the F's combined. So here's all of our quantum numbers together in a table. What you would need to be able to recognize is like what electron a set of quantum numbers is describing, or which one is possibly incorrect. So for example, if we have our first principal quantum number of 1, then our angular momentum number can't be negative 1. So that would be incorrect. But let's say it was 1 and we had 0, 0, negative 1/2. So that would be a description of an electron in an S orbital. Let's say we had 3. So on our third principal energy level, we have an L of negative 1. Excuse me, an L of 1. M sub L of negative 1, and then 1/2. So this is my third energy level. It must be a P orbital. It's one of the P orbital orientations, and then the electron is 1/2. So this is electron, in a p orbital. So what our quantum numbers lead us to is that no two electrons of the same atom can have the same exact 4 quantum numbers. Because even if they had the exact same, like let's look back at this orbital here, or this electron there, we could also have 3, 1, -1. Those are all exactly the same, but this time it would have to be -1/2. And that would be the other electron in the same p orbital as this one, but it has to have the opposite spin, which is how we get to that. You can't have 2 of the exact same sets of quantum numbers. This also leads us to being able to do electron configurations and orbital diagrams. So Pauli exclusion principle, what we just talked about, we can't have more than 2 electrons in an orbital. They have to have equal and opposite spins. The off-bound principle tells me that electrons are always going to fill levels or orbitals with lowest energy first. And then Hund's rule tells me that they're always going to fill a sublevel one at a time before doubling up. So remember, sublevels are our S, P's, D's, and F's. So I like to think of these rules kind of like a hotel. So we're always going to fill the lowest levels of the hotel first. So we're going to go, first floor. Let me get my pen. It's been out of its little thing too long, so it won't recognize it. So first level, second level, third level. So we're going to go from the bottom up. Then we have the idea that, okay, if you were going, let's say, on like a trip with a bunch of strangers that you didn't know, you would prefer your own room. So we can think of that like, okay, we're going to put one person in a room first before we were to double up. Then if we do have to double up, you can think of it like, okay, I don't really want to catch any kind of weird germs this person might have, so I'm going to sleep in the opposite direction as them. So that's kind of our electrons having equal and opposite spins. So what you saw on the last slide with the arrows and electron configuration does not get that specific. Electron configuration only has the principal energy level, so the principal quantum number, the orbital shape, so S, P, D, or F, and then it's just the total number of electrons. So it does not get into the specific orientation. So what I mean by that is, let's look at sodium. If I was doing its orbital diagram, I would have 1s, 2s, 2p, 3s, and then I would put its electrons in each individual orbital. But notice, for an orbital diagram, each of the 6 electrons that are in the p orbital are in their actual individual orbitals. Whereas for electron configuration, we just say that there are 6 electrons in the 2p sublevel. We don't actually get specifically into the 3 different p orbitals. We can also write electron configuration in what we call shorthand, which is where we just replace this first part, the core electrons, with the preceding noble gas. So if you look on a periodic table, the noble gas that comes before sodium is neon. So we just replace all this 1s2, 2s2, 2p6 with neon. And then if I didn't make a typo, this would say 3s2. So hopefully what a lot of you remember is using the periodic table to help us with electron configuration, because it's laid out with our different orbitals. So as I mentioned, when we were talking about our quantum numbers, the principal quantum number is just the rows or the periods. Something to point out though is that d orbitals are always 1 energy level less and f orbitals are 2 energy levels less than where they're listed. Because they found that 4s actually has less energy than 3d. And so when we're using our periodic table, you just always remember 4s, and then come next is 3d, and then 4p. So our first number in our electron configuration is always our principal energy number. And then, of course, s's can never be greater than 2. So max of 2 in an s orbital, max of 6 in a p orbital, max of 10 in a d orbital, and max of 14 in an f orbital. And so if we were doing a electron configuration for, let's say, oxygen, we have 1s2, 2s2, and then 2p, 1, 2, 3, 4. So we just use our periodic table to count. If we want to do one with a d orbital, let's say cobalt, we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, 1, 2, 3, 4, 5, 6, 7. So 3d7. So that would be for cobalt. If we wanted to do its abbreviated noble gas configuration, we go up to the previous noble gas, which is argon, and we would put argon in brackets to represent everything up to this point, and then we would continue with our 4s2 and 3d7. When you're looking at electron configuration, something else to note is you can always see where your valence electrons are, because they're going to be the number that are in the highest energy levels out. So for oxygen, we know oxygen has 6 valence electrons, and we can see that here, that there's 2 and 4 in the highest level out. When we look at cobalt, we'll see that its greatest energy level is actually the 4 here. So it has 2 valence electrons, which is why most transition metals are +2, because they're going to lose those 2 s orbital electrons first. But now we know some transition metals can lose their d orbital electrons, and that's how we get like +3, +4. And we'll talk about that some more later. Okay, so let's do a couple of practice problems with electron configuration and orbital diagram. I'm going to do sulfur, and we'll do zirconium. So for sulfur, we obviously have 16 total electrons that we need to account for. Just like every single element, we always have to start at the lowest. So 1s2, 2s2, 2p6, 3s2. And then our last electrons are in the 3p orbital, and we have 4 of them. So we're going to have 3p4. If we draw this out in the orbital diagrams, 1s, 2s, 2p, 3s, 3p, we would have all of these are full, and then each of the p's have 1, and the last one is, or excuse me, the last electron is doubled in the first. So for zirconium, we have 40 total electrons to take care of. If we want to do the long full electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, remember D is 1 less, 3d10, 4p6, 5s2, and then 4d2. If we wanted to shorten that with the noble gas configuration, we go to the previous noble gas, and then we replace all of this with that noble gas, which is krypton, and then 5s2 for d2. For the orbital diagram, so you can take a minute, draw all these out. And then, of course, everything is going to be full until we get all the way to those 4 d orbitals. And we only have 2 electrons there. Okay, so Coulomb's law plays into all the atomic structure things we've talked about prior, but it's really important in the next 2 concepts when we talk about photoelectron spectroscopy and periodicity or periodic trends. So Coulomb's law states that the electrical force between 2 charged objects, so that of course is F here. So the electrical force between 2 charged objects is directly proportional to the product of the quantity of charge and inversely proportional to the square of the separation distance. Okay, so that's a lot of fancy words. And good news is you're never going to have to quantitatively use Coulomb's law. You're not going to be plugging in any numbers. We're not in physics. We're not calculating force here. We're using it qualitatively to understand conceptually how the structure of the atom works, how electrons are removed, so on and so forth. So the big takeaway that you have to have from Coulomb's law is that force is directly proportional. So if you haven't picked up yet, this little guy means directly proportional to the charge. So makes sense that the force is going to be greater when the charge is greater. So I like to think of this like magnets. So the bigger the magnet, the bigger the force holding the magnets together. However, force is inversely proportional. So that's what 1 over means. So 1 over is inversely proportional. So force is inversely proportional to distance between the 2 objects. Again, if we think about our magnets, the further our magnet is away from the other magnetic object, there's going to be much less of a force of an attraction between them. So we think about this most often when we think about the nucleus, the force of attraction between the nucleus and electrons. And we think of this a lot when we're looking at the force of attraction between anions and cations. So we'll see Coulomb's law come into play when we're talking about, electrons that are farther away from the nucleus. So greater distance have less force. Just like electrons that are closer to the nucleus are going to be a higher force. When we talk about anions and cations, something with a +2 charge is going to have more force between it and something else than something with a +1 charge. Okay, so our next concept is photoelectron spectroscopy, which requires us to understand the photoelectro effect. So what we figured out is when we strike a piece of metal with a photon of light, with sufficient energy, an electron is actually emitted from the surface, so one of the electrons of the metal. So if you remember from our puzzle, we used the example of kicking a soccer ball out of a ditch. So we had a ditch, we had a person down in there, and we had a soccer ball. And we said, let's say it took 45 joules to get that soccer ball out of the ditch. If the person kicks it with 20 joules, nothing happens. The soccer ball rolls back down. If the person kicks it with exactly 45 joules, the soccer ball gets to the top and then stays there. Because the soccer ball was given enough energy to get to the top of the hill, but it was not given enough energy to then have kinetic energy left over to continue moving. However, if we hit it with 60 joules, then the soccer ball would go out and have 15 joules of kinetic energy left to roll. So the same idea applies to these photons of light. So, for example, you see here that when 700 nanometer wavelength of light, which would mean it's got the lowest frequency, while 400 would have the highest frequency, which means it would also have the highest energy. No electrons are ejected. So that's like our first example of the soccer ball, where we hit it, but then didn't have enough to eject an electron. However, 550 nanometers and 400 hit it with enough for the electrons to then have kinetic energy when they are released. And so what we can use this for is we can know the energy of the photon of light, and we can measure the energy the photon has, or excuse me, the electron has after it is ejected. So we can subtract that, and that will give us the ionization energy of the electron, the amount of energy that was holding the electron into the nucleus. This is equivalent to the 45 joules it took us to remove the soccer ball from the ditch. So down here in this 60 joules example, we knew that we kicked it with 60 joules. We had 15 joules left. That gives us 45 joules is what it took to go out of the ditch. So this is what scientists use. To determine the ionization energies of electrons within an atom. And so here we have the focused beam of light, so we would know exactly the energy within that beam of light. And it's hitting this silicon sample here, and it is ejecting electrons, but you notice the way they depict that here is by different sizes of arrows. Those electrons are coming out with varying speeds. And so when they hit the detector, that detector can analyze what the kinetic energy of those electrons are, and it puts out this graph that shows different peaks for the different electron kinetic energies that it was measuring. This page summarizes what we just talked about in the previous diagram. So photoelectron spectroscopy is used to determine the relative energies of electrons in individual atoms. So high energy photons directed at the sample, then the kinetic energies of the electrons ejected are measured. So then we can determine the relative energies of the electrons. You'll see kind of the same formula, so to speak, that we talked about prior. So we can figure out the energy of the electron by knowing the energy of the photon that we shoot at the sample and then subtracting the measured energy of the electron that's ejected. So when we do that, we get a printout of a graph that looks like this. And you'll notice the different peaks. And the peaks represent the number of electrons, or the intensity, the amount of times that the detector was struck with electrons of that exact energy. And so we notice that the peaks are relative to one another, and they're always going to be like that. And so what you'll notice is we always start with a peak that represents 2 electrons, because this is going to be our 1s orbital. And so the maximum amount of electrons in an s is always 2. So the next was always going to be our 2s. Now we have our 2p. And so you'll notice that this is about 3 times the size of the 2s because there are 6 electrons in this 2p. Note, we're talking about sulfur here, and so for sulfur we have 16 total electrons. So then we're back to 3s, and then in our 3p, sulfur has 4 electrons, which we can also tell because it's double the size of the one that had 2 electrons. So here is our 1s2, 2s2, 2p6, 3s2, 3p6. Oops, I'm sorry, 3p4. So this photoelectron spectroscopy also further proved that quantum model that our electrons are in very discrete energy levels and nowhere in between. A couple other things to point out about these graphs is they almost always start with the highest energy on the left-hand side and they go down. And so that's backwards, obviously, to how we view most graphs. But the reason it's written like this is because every single atom is going to start with your 1s electrons down here with the highest energy. Why do they have the highest energy? Because they're closest to the nucleus. And so as we go atom to atom, we're only going to be adding electrons this way. So it makes sense to start with the highest and go down because as we add electrons, they're always going to have less energy than these first closest to the nucleus. So looking at a few examples, down here we've got fluorine and boron. And so you'll notice that for fluorine, we've got 9 total electrons. So we have 2, in a darker color, 2, 2, 6. So 9, oops, not 6, 5. So 5, 6, 7, 8, 9. So there's our 9 total electrons in fluorine. Boron only has 5, so we've got 2, 2, and 1. So you'll see again our relative peaks. These both have 2, so they're the same size. These both have 2, they're the same size. This one's about 5 times taller than this one, and this one's half of this one. So all of them are relative based on the number of electrons. Something else that we want to point out is you notice the location of the peaks. So this is 1s electrons for fluorine, and this is fluorine, and this is 1s electrons for boron. So you'll notice the fluorine one is further to the left, so it has higher energy. That's because fluorine has 9 protons in its nucleus, while boron only has 5. And so fluorine is going to have a tighter hold. Remember Coulomb's law. It's going to have a tighter hold on its electrons, and so it's going to take more energy to remove those 1s electrons when compared to boron. You could be asked to identify, and of course I left this chlorine in here, but you're going to be asked to identify possibly what a photoelectron spectroscopy graph, which atom it's representing. And so we can do that by just counting up the electrons. So we have, here's our 1s2, 2s2, 2p6, 3s2, and I notice that, all right, if this is 6, 1, 2, 3, 4, 5, 6, then this one's 5. So then I have 3p5. So if I'm talking about 3p5, I'm talking about chlorine. So you may be asked to identify an atom or an element based on its photoelectron spectra, or you could be asked to explain, for example, why this peak for fluorine is here, but this one is here for boron, whatever I'm talking about. Now we're going to talk about some periodic trends, most of which should be review for you. Quickly, just to make sure we know our terms, if we're going up and down, we're talking about a group. So groups are also known as families. Those are the columns on the periodic table. The rows on the periodic table are periods. So those are going to show our trends as we move left to right. If you are talking about similarities, elements within the same group are always going to be the most similar to one another. That's kind of why we call them families. So if you're ever asked which two elements are going to be the most similar in their properties, their reactivities, their characteristics, you're always going to go with the ones in the same group. Okay, my first periodic trend is atomic size. And so atomic size is defined as half the distance between two nuclei. Because electrons are constantly moving and atoms are mostly empty space, it's kind of difficult to measure the size of an atom. So instead they define it as half the distance between the two nuclei. So that kind of gives us an idea of the atomic size. So it's going to increase as we go down a group, and it's going to decrease across a period. So what that means is that overall atomic size is the largest in the bottom left corner of the periodic table. So you can see this as we look at the halogens, we increase as we go down that group. So if we think about why that's going to happen, why do we get smaller as we go left to right on the periodic table, even though we're adding electrons? And we got to think about that Coulomb's law and the effective nuclear charge. So effective nuclear charge is how much pull the nucleus is actually having on the outermost electrons, taking into account things like shielding and electron repulsion. And so any inner electrons are going to shield the most outer electrons. So we can think of it like, if here's our nucleus, and we have different shells, all of these electrons in here are shielding these electrons or blocking them from the nucleus's pull. And so that's going to reduce that effective nuclear charge on those outer electrons. So that's why as we move from left to right, we're actually getting smaller because we're adding neutrons, we are adding neutrons, but we're adding protons in the nucleus, and it's going to pull those electrons closer and closer together. But as we move down a group, it's going to get bigger and bigger, and you've got less of an effective nuclear charge on your outer electrons because they're further and further away, and we have more and more inner electrons to shield. If we want to look at a couple interesting parts of the trend of atomic radius, so if we're looking at this graph, it's graphing all of the atomic radii for the different elements. So we'll see, just like what we expected for lithium, sodium, potassium, rubidium, cesium. So as we go down the first column, or the first group, we're getting larger. But as we move across a period, so lithium, this would be beryllium, this would be boron, carbon, nitrogen, oxygen, fluorine, and then neon, we get smaller. But we will notice a couple of interesting little changes. So for example, kind of right here, we have like a little bit of an alteration in the trend. And if we look, that's because for oxygen and fluorine is the first time that we double up in our orbitals of the 2p orbitals. So we've got a pen died. Hold on. So 1s, 2s, 2p. So if we're looking at how we're adding in the electrons, so 6, that's carbon, that's nitrogen, but now I'm up here at oxygen and fluorine. That's the first time that we've doubled up. So that's why we have this little weird change in the trend for the last couple, because of doubling up, and that repulsion causes the pull to be just less, a little bit less, and so they kind of go against the trend. Ionic size. Of course, ionic size is going to follow atomic radius when we're talking or comparing different elements to one another, but what this is really focusing on is comparing neutral atoms to their cation or their anion. So cations are always going to be smaller than the neutral atom, because how do we form a cation? We lose electrons. So when we lose electrons, we now have a more effective nuclear charge. So let's think about something like the example down below is aluminum. So when aluminum is going to lose its 3 valence electrons, when it does that, all of its remaining electrons are now way closer to the nucleus, and it's going to be able to pull it in tighter. And so the cation is much smaller than the neutral atom. Of course, just the opposite is true for anions. They're going to be larger, because how do we form an anion? We gain electrons. And so when we add electrons, so let's say for sulfur, which normally has 6 valence electrons, when it adds 2 more to become sulfur 2 minus, we now have more repulsion between these electrons, and so the effective nuclear charge is just a little bit less, and so it's going to be larger than the neutral. So for cations, the neutral is bigger. For anions, the negative ion is going to be larger. Moving on to ionization energy, the overall trend for ionization energy is going to be just the opposite of atomic radius. Ionization energy is the amount of energy required to remove an electron. So think ionization, creation of an ion. So how much energy is it going to take to remove that electron? So it's going to decrease down a group. So it's going to decrease down a group, so it's highest at the top, and it's going to increase across a period. So what that means is our overall trend for ionization energy goes to the top right corner of the periodic table. So we do have what we call subsequent ionization energies, meaning for the first ionization energy is going to be to remove that first electron. Then the second ionization energy is going to be removing the second electron. Those are always going to increase. So that means that the ionization energy to remove the second electron is going to be greater than the first electron. Then the third one would be even bigger than the second one. And this makes sense because each time we remove an electron, all the nuclear charge is now redistributed between less electrons, and so it's going to be stronger. Something to note is that if we have a huge jump, so if you see a huge jump in ionization energy, you have moved into core electrons. So for example, they're always going to increase. But let's say that we see first ionization energy, second ionization energy, and then the third ionization energy is like thousands or hundreds higher. Then that means we probably have a +2 cation, so something like magnesium, because when we got to that third electron, we were now in an inner level, and so it was way higher. If you see a jump happen after the third, then we've got a +3, so something like aluminum. If you see a huge jump after just the first, we've got a +1 ion, so something like sodium. So looking at some interesting little changes to the trend for ionization energy, we have these little like lightning bolt type things. So we see that overall what we expect, so we go down a group. So let's look at the noble gases. We go down a group, we're getting lower in ionization energy, which is what we expect. But when we move across a period, we'll notice there's a couple little switches. So we have lithium, beryllium, but then boron actually goes down before going back up, and then from nitrogen to oxygen, we also went back down before going back up. So let's try to explain those. So if we notice what changes from beryllium to boron. So if we look at the electrons, the last electron in beryllium is in the 2s orbital, while the last electron in boron is in the 2p. So 2p is just slightly farther from the nucleus. So it's going to be just slightly easier to remove. So that's why boron has a lower ionization energy than beryllium. Same thing up here between nitrogen and oxygen. The last electron for nitrogen, they're both in the 2p, but for nitrogen, they are alone in their orbitals, while oxygen has the first one to be doubled up. Sorry, it's kind of hard to see. So oxygen is the first time it's doubled up, which is why oxygen is slightly lower than nitrogen before the trend continues to move upward. Electron affinity is the energy change for the process of adding an electron to form an anion. So you can really think of this like how badly does that atom want to gain an electron. So it makes sense that that's going to be the highest with our non-metals because those are the ones who typically form anions. So an interesting exception to note though is we're going to decrease as we go down a group, except the second element in a period is going to have lower than any other ones. So you'll notice that like right here for beryllium, or here's magnesium. So they're going to have the lowest, and that's because their last electron would be added to an s orbital, which is so small that it really can't happen, and so it's almost impossible to do. So that's why they're going to have the lowest.